It is almost impossible to talk about analog circuits without including an op-amp. Here, the top plot is the microphone signal and the bottom is the output with 5 times amplification.
It comes to inverting amplifier, one should know it will be amplifying signal, but output is getting inverted over here. Inverted means here you see we will be having negative gain. So output, that is minus of A into V in. This minus sign that explains this is inverting amplifier and gain is A. So output, that is out of phase with respect to input. You see input is this. Out of phase means signal will be like this. So that is how signal is appearing and that is having gain A. So with inverting amplifier, phase shift of 180 degree is there and amplification factor A that depends on type of amplifier and type of feedback. If you talk about non, you see gain is plus A. So output, that is having zero phase difference with respect to input. So you see input is weak signal, output is amplified by factor A, right? There is no phase difference. Here amplification factor A that depends on type of amplifier and type of feedback. It will be zero phase difference. So unity gain circuit means what? Gain is output by input. As output and input both are equal, gain is 1. So you can say it is unity gain circuit. And it is having zero phase difference. You can observe here, output and input both are having same phase. If both are having same phase, then you can say phase difference is 0. So voltage follower circuit means what? It is unity gain circuit with zero phase difference, right? So voltage follower is having gain that is equals to 1. Now how to have voltage follower using operational amplifier? So let me explain you that. See, to have voltage follower, here I'll be using non-inverting op-amp. Non-inverting op-amp means what? Here input is given at non-inverting terminal. Non-inverting op-amp means input is given at non-inverting terminal. Non-inverting means plus terminal. So input is given to non-inverting terminal. And we have negative feedback. With this negative feedback, we have feedback resistance that is equals to 0. We have feedback resistance that is equals to, and RF is 0. So you can say gain is equals to 1. If gain is 1, then you can say output that is equals to input. Input is Vs over here. So simply you can say this is voltage follower circuit where RF resistance is 0 in negative feedback and input is given to non-inverting terminal, right? Correct. As I have told you, same circuit can be used as a difference amplifier. If you want to use this circuit as a difference amplifier, then output will be difference into amplification factor A. If your circuit is functioning as a subtractor, then this gain should be equals to 1. Now I'm going to derive output equation over here. To derive output equation, first of all, I'll be considering output due to input VA. Now here we wanted to have output due to input VA. Let us say that output is VOA. So here we need to ground this VB as VB is 0. So here I'm providing VB is equals to ground, right? Now what is my output VOA? So my output VOA that is happening based on non-inverting configuration. If I say at this node, let us say voltage is V dash, then VOA will be V dash into gain due to non-inverting mode. See, with negative feedback, with non-inverting mode, what is my gain? Gain is 1 plus RF by R1, where RF is feedback resistance and R1 is this resistance. So VOA in non-inverting mode, that is V dash into 1 plus RF by R1. Now what is V dash? See, V dash that can be calculated as per voltage divider rule. V dash will be how much? V dash will be VA into this resistance that is R3 divided by addition of these two resistance that is R2 plus R3 and into this gain that is my VOA, right? So you see my output due to input VA that is VA into R3 divided by R2 plus R3 into 1 plus RF by R1. Gain in inverting mode with negative feedback is how much? Minus RF by R1, right? So here VOB that is minus of VB into RF by R1. So now we have output due to input A and input B, right? You see we have calculated both. So what is my total output? Total output that is algebraic sum of output due to VA and VB. Let me write that. VO is equals to VOA plus VOB. Here, if you observe VOA, that is this. So that is VA into R3 divided by R2 plus R3 into 1 plus RF by R1. And VOB, that is minus VB into RF by R1. Let us simplify this. See here, we are just taking LCM of R1. So this equation will be R3 divided by R2 plus R3. And here we will be having R1 plus RF divided by R1 minus VB into RF divided by R1. Now with this, see we wanted to have simplified equation of this and that has to be there in form of VA minus VB into gain. Now here, if you observe this VB term that is having RF by R1 and we wanted to have VA term in terms of RF by R1. Right? So what we can do is we can assume few basics. You see we want to cancel this R1 plus RF with this. So if you assume RF is equals to R3 and if you assume R1 is equals to R2, then you can cancel out these two terms, right? And you can substitute R3 is equals to RF. So your simplified equation that will be VO is equals to VA into R3 is RF now divided by R1 minus VB into RF by R1. So you can say your output will be RF by R1 into VA minus VB, right? That is my output over here. Now see earlier I have told you this same circuit that is working as a subtractor if RF is equals to R1 and that is working as a difference amplifier where gain is RF divided by R1, right? So you see I have told you earlier this circuit that can be functioning as a subtractor if A is equals to 1 and same circuit that one can use as a difference amplifier where this gain A that is RF by R1 that is RF by R1, right?
This type of circuit can be used to drive the LEDs because here once you set the value of this resistor R and the input voltage V in, then the current that is flowing through this LED will be constant. So now if you change the value of this input voltage, then the current that is flowing through this LED will change. And you can use this circuit to test the brightness of the different LEDs for the constant
input
current.
Signal with respect to time. So if your input is V in over here, then output will be differentiation of input with respect to time. this differentiator that we use it to identify high frequency components from input signal. So here, whatever high frequency components that is there with input signal, that one can identify with the use of differentiator. Like if you observe here, see this is input, where at this portion, input is constant. As if input is constant, it does not have high frequency components. But here if you observe, input is varying fast. So as input is varying fast over here, these are the lines which is having high frequency components. So if you observe output of this signal, then in this you see when falling edge is there, at that time output is having negative spikes, and when rising edge is there, at that time output is having rising spike. So one can say differentiator circuit that is used to identify high frequency components. See, differentiator is essentially high pass filter.